All right, everyone. So we're going to look at another example of, sorry, we're not going to look at an example, we will eventually, but look at another idea in integrating over general regions, doing our double integrals over general regions. So suppose I have a function f of xy. So we're going to focus on the region we're integrating over first. So we can just think of this as some arbitrary function that we want to integrate over the region D, where D is described like this, right? It's all the points xy such that x squared plus y squared is between 4 and 9. And I'm going to actually add one more condition just to make this easier to draw. Let's say that y has got to be positive. Okay, just make this picture a little bit easier to draw. All right, so let's take a look at this region. All right, so I'll draw a couple of axes. Oh wait, I just realized something. I don't need to take this away. I can use the drawing system here to make this drawing easier. Okay, so sorry about that. I've taken away that restriction. What is the point? What are the points x squared plus y squared less than or greater than or equal to 4 and less than or equal to 9? Well, if we think of the points that are where x squared plus y squared are greater than 4, that's going to be all the points outside of a circle with radius 4. Sorry, radius 2, right? So let's that be that circle. And then x squared plus y squared equals 9 is going to be all the points that have a on a circle with radius 3. Right? So what that means is this region is all the points that are either on the inner circle or the outer circle or in between the two of them, right? So it's going to be this little ring that we've got here. Okay. Well, if we were to try to integrate over this, it's going to be quite a headache, right? We would have to use, right, we could bound x or y between some set of numbers. Even if we only focused on, say, one corner of this, at some point we're going to have to bound a function, bound one of our variables between two functions, right? We're going to use something like, right, we can bound one of the variables. Let's say we bound x between a and b, and then y will be bound between these two functions, whatever they are, right? But these functions g1 and g2 are going to be things like, something like, you know, in this case, for instance, the bottom function would be the square root of 4 minus x squared, and the upper function would be the square root of 9 minus x squared, right? That's how we could do this portion of the circle. And then we'd have to set up some other functions down here. There'd be all kinds of things we would need to do this, right? And then when we integrate over y, these square roots with x squareds are going to show up all over the place. And while they might be integrable with some of the methods we have, things might get complicated. So here's a thought. Let's describe this differently, right? Remember, let's erase some of this stuff. When we see things in a circle like this, one of the things we might think about is polar coordinates. Right? Remember what polar coordinates are. They describe points instead of by how far they are horizontally from the origin and how far they are vertically from the origin. Instead, they point in the direction, or they tell you the direction the point is living, and then how far away from the origin in that direction. And so things that are circular tend to be really easy to describe this way. So here, I can describe this region D using r theta, right? this circle is now going to be the set of points where r is between 2 and 3. The radius is between 2 and 3. And theta is going to be between 0 and 2 pi. Really, any 2 pi interval would do, but this is the most obvious choice to use. Okay. Now, notice how much easier this sort of set of inequalities is, right? There's interaction between x and y here. This is equivalent to what a rectangle looks like in rectangular coordinates, right? You just have each variable bound between two numbers, which is exactly what we have here. And in fact, we call this, things of this form, a polar rectangle, right? Because it takes each variable and just bounds it between two numbers. And so even though the shape is not what we call a rectangle, this expression of it is exactly the same, okay? So let's remind ourselves of one of the relationship between polar and rectangular. We can relate them by these equations. We know that x squared plus y squared equals r squared, and we know that x is equal to r cosine theta, and that y is equal to r sine theta. Okay, so we're going to need these relationships in a little bit, because what we're going to do is we're going to, instead of expressing, as I did here, instead of expressing this region in rectangular coordinates, I'm going to use polar coordinates, because it will turn out to be easier, but we need to do a little bit of work first before we're ready to do this. So let's get to work. All right, so here's what we're going to do. First, let's imagine, so I'm gonna be more general now than this circle here. Imagine I have a region that I'm going to express, so a polar here's a polar rectangle. Let me make it a little bigger to make this easier. All right, so I'll have to draw a bunch of this by hand now. So by a polar rectangle, what I mean, so let's label some of this. What I mean is we have our radius bound between two numbers and our angle bound between two numbers. So for instance, this angle I'll call alpha. This angle I'll call beta. So this line here is the line theta equals alpha. This line here is the line theta equals beta. And I'm only really going to look at the region, right? This line here, let's call this r equals a, and this line here, r equals b. So this little region that I've drawn is the region r theta, where r is between a and b, and theta is between alpha and beta. Okay, so it's, again, a polar rectangle. The picture looks very different, but these expressions are very familiar for how we describe rectangles in rectangular coordinates. Okay, so this is our general region that I want to integrate over. And we're going to use a very similar idea that we use in rectangular coordinates, which is to split this up into smaller regions. Let's see if this will let me do it. Right, so imagine I'm drawing these perfectly, they all should be like aligned to the center, right? They should go back to the origin if we drew them all the way. This is like chopping up our rectangle into little squares. We divide along theta, right? So each of these represents a different angle. And now each of these will represent a different radius. So I'm chopping up the intervals into these little squares. Okay. So let's label some things. So for instance, this right here, we can call R naught equals A. right? And we'll go up to R sub, let me see what I use so my notes match, make this a little easier for myself. R sub M is equal to B. This would be R1, R2, and on and on and on. So we could obviously count these, but I'm imagining there's an arbitrary number here. We can call one in the middle R sub I. The same thing happens for theta, right? I'm going to divide up theta, right? This line here is theta naught, which is going to be equal to alpha. Over here, I have theta n, which is equal to beta. I would have theta 1, theta 2, and on and on and on. Anywhere in the middle, I'll just call it theta sub j. Okay? All right, so let's pick one of these little squares. I'll pick this one here. And let's figure out the area of this square, okay? Let's figure out the area of this square. So let me draw this square a little bit bigger out here. Right, here's my square. All right, so it's going to go from, let's say this line here is theta j. This will be theta j minus 1. So those are the two radial lines defining the angle. And then this radius in here we'll do as radius I minus 1. And this will be radius R sub I. Sorry, not radius, but R sub I. And R sub I minus 1, right? So we're taking a little piece, just like we would look at rectangles between X sub I and X sub I minus 1 and Y sub I minus 1 and Y sub J minus 1 and Y sub J. We're splitting up there. So I'm just drawing this piece bigger over here to make this a little bit easier, okay? We can choose, we're going to choose a point in the middle to represent this one. We're going to do the same kind of approximating thing where we can think of rectangles above these things or extruding these things up to our service for approximations. Let's choose a point here that I'll call R I star theta j star. And I'm going to choose the midpoint. Again, this is just to make some of the computations easier. Nothing I'm doing right now depends on that. It's just going to make the algebra easier. The result is the same, but sometimes more difficult if you choose different points. So R sub I star is going to be the midpoint of these two R values. So 1/2 R sub I plus R sub I minus 1. Same thing with theta j star is 1/2 theta j plus theta j minus 1. All right, so you add them together, divide by 2, we get the average between them, right? So the coordinate here is lined up in the middle here. So that's our center point of these two things. So here's our next idea. I want to know the area of this little, it's not quite a rectangle, it's a polar rectangle. So what I'm going to use is the area of a sector of a circle. Okay? So in general, the area of a sector of a circle is 1/2 R squared theta. Okay? When we're in radians, and this is something from we've seen in the past. So I'm going to not explain where this comes from. I'll let you work that out on your own. But what we're going to do with it is imagine the sector that I've drawn up here, or the piece we're working on. This piece up here, I can think of as I can take a sector that has, let's see, the angle will be theta j minus 1. Right, that will be the angle between, because it's between these two thetas. That's how much is in between them. And I'll take the area of the full sector, the one that goes from here to here, and then subtract the sector that's smaller. That will leave me with this area here, right? So this is now, the starred picture is a picture of this square right here. This sector drawing that looks like a candy corn is if I drew this sector all the way from following these points down to the origin, right? So let's write this out. We're going to have, so the area, what do I want to call it? I'll call it IJ. Let's call it delta area IJ, is going to be, so 1/2, I'll take R sub I squared, and then we multiply that by theta j minus theta j minus 1. Let's just call this delta theta. That's the area of the big sector here. Then I minus 1/2 R sub I minus 1 delta theta. Oh, and this thing is, of course, squared, right? Because this is our radius R sub I minus 1. This is the radius R sub I. Okay. So now, let's do a little bit of algebra. I get 1/2 R sub I squared minus R sub I minus 1 squared delta theta, which is 1/2 R sub I plus R sub I minus 1 times R sub I minus R sub I minus 1 delta theta. Well, what is this piece right here, 1/2 R sub I plus R sub I minus 1? That is exactly R sub I star, that midpoint. R sub I minus R sub I minus 1, we can call delta R, and then we've got delta theta. So each little piece of area has this expression. The center point, the R value of the center point, times the change in the radius times the change in theta. Okay? So what do we do for our approximating rectangles that we draw over this, right? Well, our volume is going to be approximately, we're going to have to do another double sum like we did when we did these Riemann sums, when we did this with rectangular coordinates. So we take the sum from I equals 1 to m, then the sum from j equals 1 to n. I think that's the letters I used, I hope. Yeah, it looks like it. And then we take the value of our function. All right, I'm going to leave this open for a moment. We'll take the value of our function times this little piece of area, right? So remember what we're doing. We're multiplying this area times the height of the function above it. So here's the height, and the area below it is what we've called delta A I sub j. All right, well, what goes in here? Well, we know it's f of x, y, but we have this relationship for x and y. So instead of x and y, I can write, I'll use the center point, r I star cosine theta j star, and r I star sine theta j star. Sorry, that's cramped. I didn't leave myself quite enough room. Okay, let's finish this out. Give myself a little more space here. All right. So what does this work out to look like? We get I equals 1 to m, j equals 1 to n, and we have f of ri star cosine theta j star, ri star sine theta j star, and then delta ij is going to be ri star delta r delta theta. Okay. Well, of course, in the limit, this becomes an integral. And the integral will look like this. When we take the limit of this thing as m and n go to infinity, we get the integral as we go from alpha to beta, the integral as we go from a to b. So these are the limits on theta and r. We get f of r cosine theta, r sine theta, and r dr d theta. Okay. All right. That was a whole bunch to get there. Okay. But here's the takeaway. If we are trying to integrate, so let's give this a little bit of conditions here. If f of xy is continuous on a polar rectangle r is equal to r theta, where r is between a and b, and theta is between alpha and beta, where let's put in, sorry, one more condition. We're going to take r to be positive, right? There's no reason to choose negative r's. It just makes, so pardon me for leaving that space. And we also need to have that 0 alpha minus, or beta minus alpha is between 0 and 2 pi. So we're moving in the positive direction, and we don't go around the circle more than once. We'll be kind of like doubling up the volume, adding itself on top of itself, okay? So all these conditions are just to make it easier on us, like if r is negative, it goes in the opposite, it just makes everything confusing. So we will only use this when we can describe the shape using positive r values and angles that have less than or equal to 2 pi difference between them, and we're moving in a positive direction. Then we can simply substitute r cosine theta and r sine theta in for x and y in whatever function we have, and dx dy becomes this, okay? This was not a rigorous proof of this. In reality, what we're using is a change of coordinates, which is like a higher dimensional version of the substitution rule that you've learned. And what happens when you do a u sub, you substitute u for x, or whatever expression you have, right? U for some expression of x, and then dx is some expression of du. Well, this is the version of that in higher dimensions. Dy dx gets replaced with r dr d theta. Just like if you do u equals x squared, dx becomes 1/2 du, right? You get some kind of thing happening. 1/2 x, x dx becomes 1/2 du. So this is how this is going to work out. So let's do an example, all right? Because I know often this is pretty confusing when it's abstract, but let's get ourselves an example. So let's take a look at the function f of xy equals e to the negative x squared plus y squared. And let's take the region D to be the semicircle centered at the origin, let's say with radius 2, where x is greater than 0. So what I mean is, here's my xy plane. The region we care about is going to be the right half of the circle centered at the origin with a radius of 2. Okay, so that's our region. Okay, so this is a polar rectangle. So let's describe it that way. This is going to be the points r, theta, such that r has got to be between 0 and 2, right? So as we go from the center out, we're covering every value of r between 0 and 2. And theta is going to be between negative pi over 2 and pi over 2. It's not the only way to do this, right? I could describe this as 3 pi over 2 to 5 pi over 2. There's an infinite number of ways we could describe this, but I'm going to go with this one. I think this is the simplest way to describe this region. Okay. So what else are we going to have to do? We're going to need f. Let's remember this. Our formula, when we switch to polar, it's going to be from alpha to beta, from A to B, f of r cosine theta, r sine theta, r dr d theta. So with this expression of d, I now know exactly what A and B and alpha and beta are, right? They're the limits on the radius and the angle. Let's take a look at this piece, f of r cosine theta, r sine theta. So f of r cosine theta, r sine theta is going to be e to the negative r squared cosine squared theta plus r squared sine squared theta, which of course we can factor out the r squared, and then cosine squared theta plus sine squared theta becomes 1, and we get just e to the negative r squared. Okay. Now I also want to point out, if we were trying to integrate without switching to polar, the e to the negative x squared plus y squared, try to find an antiderivative of that. It's a very difficult problem to do. However, with the polar coordinates, this is going to become much simpler. So now that I have all my pieces, I can write this. Alpha to beta is negative pi over 2 to pi over 2, 0 to 2, and we have e to the negative r squared, r dr d theta. Let's concentrate on this piece. All right, so maybe I'll do this off to the side. The integral 0 to 2 e to the negative r squared r dr. Oops, I forgot to include dr. So this piece, doing that piece. Okay. So this looks ripe for a u substitution. If I take u equals r squared, then du equals 2r dr, or 1/2 du equals r dr. And I get e to the negative u, 1/2 du. Let's put the 1/2 out front. Let's change the bounds. U is equal to r squared. So this is going to now go 0 to 4. And we'll get 1/2. The antiderivative of e to the negative u is negative e to the negative u. We're evaluating from 0 to 4. And I get 1/2 negative e to the negative 4th minus a negative e to the 0, which is 1/2 1 minus e to the negative 4th. Okay. This can replace this entire red box. Okay. Now, this thing that we just computed, this is a number. 1 minus e to the negative 4th, that's a number. Multiply it by 1/2, that's a number or a constant. This whole thing can slip out front of this integral. And I just get d theta, or I can put a 1 in there if we like. This is a very simple antiderivative to take. The antiderivative of 1 is just theta evaluated from negative pi over 2 to pi over 2, which is going to be 1/2 1 minus e to the negative 4 times pi over 2 minus a negative pi over 2. So pi over 2 plus pi over 2 is pi, and then we have this 1/2. So it looks like we'll have pi over 2, 1 minus e to the -4th. And that's the integral of this function, right? So we went from a very difficult, right, this function right here, if we were to try to integrate this in the traditional way, right, we'd have something like, let's say 0 to 2, negative square root of 4 minus x squared to the positive square root of 4 minus x squared. And then we would have e to the negative x squared plus y squared dy dx, right? That expression there represents the volume we're looking for. This is a very difficult problem to do. This is a very difficult problem to do as written in rectangular coordinates. By switching to polar coordinates here, because the shape lent itself to this kind of description, it made the problem incredibly easy. It's also noteworthy, a little later we'll look at how you don't quite have to have polar rectangles, similar to how we went from rectangles to more odd shapes in rectangular coordinates. We can do that with polar. One of the other clues that we might want to switch to polar is when we see expressions like this, x squared plus y squared, which can be difficult expressions, but they become r squared, which simplifies them to some degree. So that's another hint down the road. But in any event, this is a very doable integral once we make the switch. The trickiest thing was this u substitution. Okay, that is it for this one. Thanks everybody. I will see you next time.